Next, we'll welcome our next speaker, Professor Zico Kolter, who I think a lot of us are quite familiar. And Zico is associate professor in the computer science department at ICML, and also served as the chief scientist at AI research for the Bosch Center for AI artificial intelligence, which have a lot of real-world problems, I believe. And his work spans intersection on machine learning optimization with a large focus on the developing more robust and rigorous method in deep learning. And in addition, he has worked in a number of application areas, highlighted work on like smart energy systems, and he's a recipient of many good prestigious awards like DARPA Young Investigator, Sloan, and Best Paper Awards at top machine learning conference like NeurIPS, ICML, etc. I believe actually similarly, if in our even in our research group, we even have a whitelist for the authors to every day retweet the papers on the archive and say if there are papers from actually the speakers here from Zico's group, Manju's group, and we will get quite excited to read the paper and follow up. So that's very interesting, and we are very honored to have Zico today to give us more insights about what do we mean by verifying machine learning or deep learning networks. Right, welcome.
Thank you very much for that very kind, overly kind introduction, I would say. So, this talk is about what does it mean to verify a neural network, and I think by the as implied by the quotes that I have there, you can probably guess that this. I actually I think similar to Alex's talk. This is a topic that we've worked on for a while, but it's one that I think we don't fully appreciate. I mean, we as a community, don't fully appreciate the limitations of what we mean when we talk about certifying robustness or training robust models at all, right? So I'll talk about about what I mean, but really this talk is more than previous talks you maybe have seen from me. This is actually reflects a bit of a more pessimistic attitude about our capabilities in the current field. Really both as just a warning about what we need to be careful of, in addition to hopefully somewhat of a call to action about the directions that I think are really important to go in, but not always clear, I think, how to follow those directions. So, hopefully some smart people in the audience, more so than me, can figure out how to take the next steps here. Okay, so here are my the intro slide of how great AI is, right? And I always try to refresh this slide. I think most people have probably seen these things before. So recently there's been things like AlphaFold, like DALL-E, like the latest iteration of StyleGAN that's generating. So AlphaFold is really probably actually the most exciting of all these things to me personally, just because it seems like a genuine breakthrough in scientific knowledge. Learns how to break protein structure much better than past work, and is now actually open sourced. So people have replicated these results. It really just seems like a momentous advance. Whatever that word is. This is the latest iteration of StyleGAN, and able to generate really a ton of examples of data like cats now and paintings and animals with wolves and lions and such, as well as other things that maybe are also valuable to generate, like cells from stained cells. They're normally generated under normally taken photographs of under a microscope. And then stuff like the DALL-E system that actually has people enter a text prompt. It's a really cool demo, but it's also a very limited demo. You can only select certain things, so it's unclear quite how general this is, but this is still super impressive, right? They have the system that can basically, you type something like an illustration of a baby hedgehog in a leather jacket using a calculator, and lo and behold, you actually get some of these baby hedgehogs in leather jackets using calculators, right? This is just wild. So this is amazing, right? We're sort of in this time where there's just, as I say, I update this every year, and I always have to it doesn't take too long to think of a bunch of things that happened in the past year or often in the past 3 months that, despite knowing how they work on a technical level, they still kind of blow me away. This is possible, right? So it's just, let's take some time to appreciate just how impressive some of these advances are. But of course, as we all know here, and I won't dwell on it too much, there are, oops, I think one figure is not quite appearing here, right? But there's also these huge problems of security challenges in AI systems, right? So there's adversarial attacks on these things. I actually want to show one more video too. So this is you know, I tend to use Alex's pig everywhere. I won't say the joke because I think we've all heard that plenty of times. But we've also done some work. So not only does this apply to classification within the virtual domain, we've also done some work showing that, for example, you can also apply this to object detection settings, right? So here's an example of YOLO kind of doing its thing, detecting stuff. We created some physical adversarial patch here that basically, without even overlapping with the image, is able to basically suppress most of the detections in the image. So it's the equivalent to if you're driving a car that's detecting things, could you put like a sign, a patch on a stop sign separate from everything that would actually make all the cars vanish in the road? And the answer is yes, you can, at least if you know the network structure that you're trying to attack, right? So these are sort of massive potential blind spots, no pun intended, in our models. And these aren't even the only possible attacks. So Alex also mentioned a bunch of things, so I won't dwell on this too here. Oops, let me pause this. Of these, data poisoning attacks where you can basically add synthetic data to your training examples that then, when you apply them to the real world, are able to basically very reliably fool the classifier. So if you have a stoplight, if you train a classifier with on a traffic sign database, but then you, unbeknownst to anyone else using a classifier, introduce little yellow patches on stop signs and called those speed limit signs, then at deployment time, you just have to go put a yellow patch on the stop sign and it will call it a speed limit sign very reliably. And unless that yellow patch is there, you wouldn't know that this is sort of an issue with the classifier. So to sum up, and again, I'm not going to dwell on this because I think this point has already been made by others here, is that deep learning systems are vulnerable to malicious attacks. And these really do, I believe, they definitely illustrate something fundamental about the nature of classification too, but they also do genuinely represent a security threat to the deployment and use of these systems, right? Which I think is actually pretty well appreciated, at least by this audience here. But it's something that I think needs to be understood when we talk about developing machine learning systems. So with that being said, now I want to shift gears a bit and talk about what we might be able to do about this. And on that line, I'm going to talk about sort of what the typical avenues people use to address these concerns are, which essentially is the challenge of verifying the output of neural networks. And so in other words, we can sort of more formally ask the question, like, what would it take to guarantee that deep networks are not vulnerable to adversarial attacks? You can also look at this from a more empirical standpoint. It actually doesn't, the performances vary a bit, certainly. The more empirical methods perform a little bit better, but don't have a guarantee, whereas the verifiable methods have guarantees with them. But really, actually, I don't care if we're talking about sort of empirical guarantees or certified guarantees. I'm going to talk about sort of the more formal guarantees, but really, it's a very similar question. How can we develop systems that are not vulnerable to these attacks? And one way we at least think that we can go about starting to answer this question is to formulate this question as one of verifying the input-output properties of deep neural networks. So here is a setting of a deep network, right? Or here's an illustration of a deep network. And I'm going to use this illustration to kind of say what I mean by verification, right? So basically, a deep network, takes some input space here, it maps it to some output space, and then our final classifier is like a linear classifier in this final feature space that it has, right? And by their nature, because they are nonlinear transformations here, if we take some well-defined region in input space, say, L infinity perturbation of the input image, then when we feed it through our network, what we get at the end is some nasty non-convex shape that's very hard to formally reason about. Or at least, it's doable, but it's sort of hard to do, but we'll get to that in a second. but it forms some sort of odd shape in the final layer. And then the question of formally verifying in some sense that this network gets the right answer, not just at its initial point, but at any point in this ball around it, that is the question of saying, in this final layer here, is the output for the true class greater than the outputs for any other class for all other classes and for all perturbations less than some size, right? So basically this is, the probability of the true class, is that greater than the probability of any other class for all perturbations that we want to allow for the input. So essentially what verification boils down to is just ensuring that properties like this hold for the network. And that's what verification of a deep network really is. So that's what it means, that it's a verified deep network, I guess, in the most literal sense. But how do we go about doing this, right? Because these are really complex regions of space that networks describe here. How do we practically go about verifying deep networks? And so I want to actually talk about here the two different kind of classes people have adopted, of which we've worked sort of in both to a certain extent, of how we might go about doing this. And essentially what this boils down to are two different ways of verifying the properties, or there are two different ways for formally verifying, I should say probably in a deterministic manner. There's also probabilistic verification, but I'm not gonna talk about that today. There's sort of two different ways of verifying a deep network as it's typically viewed. One is by combinatorial optimization over the exact reachable set. So if we can somehow, these, by again, the nonlinear nature of the network, are sort of nasty nonlinear shapes that we can't really easily reason about. But we can, it just takes combinatorial optimization. The alternative is that we can optimize over some sort of relaxation of this set that might be easier to verify over, but which only gives us kind of, it's incomplete verification in that it might not be sure, it might not exactly capture that final set. So let me talk about kind of at a high level, and these are going to be very quick slides here about how these two sort of methods work here. The first is how sort of incomplete verification works in deep networks, and the basic way that this works is, and there are sort of a variety of different algorithms for doing this, but I think this captures actually the way most sort of incomplete verifiers work. Is they want to form some relaxation of the reachable set. And the way you do that is you take the activations in the network and you relax, like a ReLU, for example. And I should emphasize that the ReLU and these nonlinearities are the only sort of hard nonlinear component of a network. It's the only sort of component that has to be relaxed. You take these nonlinear components and you relax them to their convex hull. Right, that's sort of the typical way you do it. And when you do that for a ReLU, for example, what this means is that, you know that you're because you're optimizing over a bigger set now, you know that you're kind of optimizing over an over approximation of the reachable set. And oops, again, this animation not quite working. And then the maximization important is now a linear program, because it's for at least for ReLUs, these sets here are linear programs. They're all linear inequalities that specify the reachable, the relaxations of the reachable set. Now, it's just that you can't really optimize over this set that easily here. So what you actually want to do is optimize over a further relaxation of this relaxation in practice, which is relates to the dual problem of this linear program, though there are other ways of deriving it as well. And it also can be derived with Lipschitz arguments or hybrid Zontope arguments, and these things essentially are there were a bunch of methods that sort of developed very similar techniques at around the same time. So this is basically how incomplete verification works, and this is how you do it. You relax the reachable set, reason about this over relaxed set, and that gives you sort of an over approximation of where you can reach. And so if you can guarantee that nothing in the over approximation sort of violates your conditions, then you're sort of in good shape. And with this, you can actually build networks that are quite good. Well, I should really qualify that are okay for things like MNIST and actually giving good verified performance, and which can also in some sense scale to slightly larger models like CFAR and such, but which don't even scale that much. But you know, there are some really big models that if you do this properly, you can get the image net size. But this is even sort of beyond what we're talking about right now. So this is how you do kind of incomplete verification. The problem, though, is that incomplete verification is inherently going to be a rough over approximation of the actual reachable set, right? It's not going to actually sort of be it's not going to give you a very good exact bound on what you can actually achieve by your network or not. So you can't really be sure that your network is or is not going to be able to reach a certain point. So the basic approach, so the good news, though, is that we can use these sort of incomplete verifiers as essentially a subroutine to do complete verification, which exactly verifies sort of the known, or it tries to exactly verify these properties of a network. In other words, sort of exactly reason about the true reachable set of the network. And the way you do this is you take these sort of approximations. Remember, we sort of relax the ReLUs to consider their convex hull. You then split them at the 0 point, right? So you sort of split, you sort of consider a network that has a certain activation always 0 or always positive and linear. And you reason about both branches. And this is exactly actually the branch and bound algorithm from kind of traditional convex or traditional non-convex integer programming. And we can do this here also for these ReLU networks, actually very, very easily. And the good news is that when we do this now exactly characterizes the non-linear ReLU network, because if you reason about one side and the other, you actually have sort of a linear function on both sides, right? Either the 0 function or just a linear function. And so you can do everything you want with the network. Now, to get this to actually work, as you would imagine for branch and bound methods, it requires a lot of additional tricks, like running this branching efficiently on the CPU and also adapting the relaxation of how we relax these splits with one more parameter that tightens the relaxation. So I really want to emphasize that this is not that simple. A lot of sort of groups are doing similar things, but to do this well, there's a lot of tricks you need. But with all these tricks, one thing that a postdoc Huan Zhang in my group is doing, as well as in collaboration, I should say, with many others. So some folks at Northeastern and at Columbia and UCLA, we're able to build this verification system that sort of incorporates all these tricks and works quite well. It's on medium scale networks. So this is actually even smaller than this is talking about still CFAR size at most here, but it can actually can scale to these things. And in fact, actually, just to sort of emphasize, just to say, have one result here about these things, in a recent competition called the verification of neural networks competition, using this approach, we actually got the top ranked score in the competition on verifying on complete verification of these networks, or actually some cases complete, some cases incomplete. But on these networks, we were able to use a technique that should get the top performing verifier. So, okay, so this is sort of the nature of what verifiers do. And now I want to talk about, though, sort of the bad news, which is that even with all these advances that we have of, the ability to verify that this network will work under all these perturbations, et cetera, I would actually argue that the pitch that I can make for these things is the worst sales pitch in history. So here's how the pitch would go, for example. Deep learning networks are vulnerable to adversarial attacks. I guess if Alex is still here, I want to ask him, do I have to really cite him, or is it part of like the public domain, this image yet? Or I guess I'll keep citing him, but maybe it can be finally part of the public domain, this image. They're vulnerable to adversarial attacks, but don't worry. Because for the low price of a 500% increase in the error of your classifier, and maybe a 10,000-fold increase in the runtime to actually do the verification, I can guarantee that for example, no perturbation of size less than say L2 norm less than 1, which is about 1 channel of 1 pixel, will change the classification result. This is literally what we are guaranteeing, the kind of things we can guarantee for image net scale classification. And so who on earth would ever do this? Because, by the way, why would an attacker be constrained to only change 1 pixel, 1 channel of 1 pixel, right? Like, these are not realistic attacks. they are arbitrary sort of threat models that we are specifying. They're formal, which is a good thing, but they're very arbitrary. Why on earth would you use this model, especially given how much worse robust models perform than traditional models? And so this puts us in a very weird state in sort of this domain of secure machine learning, which is that there is a real, genuine security threat of adversarial attacks, and I mean general robustness, but adversarial attacks in particular, right? Malicious attacks can genuinely, massively degrade the performance of systems deployed in the real world. But at the same time, despite all this work, we are nowhere close to solving the problem technically, even in the most research of all settings, let alone for practical deployments. And my genuine take on this, and I have to say, like, I mean, working in it for a few years now, I think we're going to continue to make progress. There is sort of incremental progress in how well people can build robust models. Like I think like things like robust bench are great benchmarks for doing this. But I genuinely, short of some breakthrough, which can always happen, right? I mean, maybe it's coming. I don't see us solving this problem that soon. Just my honest assessment here. So why don't people care about this? Because people aren't as bothered by this as you might think, right? People are going ahead and still deploying ML systems in practice despite not solving these problems at all. So I think as a community, we need to honestly ask ourselves, why is this happening? Why are there still applications of ML systems that we know are broken, that we know can be broken, in honestly some sort of in sometimes very security conscious settings here, or at least security relevant settings here, where people just don't seem to care about these issues. And I think we need to provide, I think as a field, we need to provide a very honest assessment about this. So there are a few possibilities I want to sort of make here. One is that just, the people doing this have their heads in the sand. They're going to pretend that the problem doesn't exist because, what could possibly go wrong when you pretend security flaws don't exist, right? And there is an element to this, of course. I think there is an element where we can sort of say, like, people are doing the wrong thing. People are taking big risks in deploying ML models. But I actually would argue that the problem is not as bad as people frequently make it out to be. And this is like, speaking from evidence now. So the reality also seems to be that it doesn't actually seem that easy to break practical deployed systems, at least not as easy as the research would suggest. And part of the reason for this, I think, is that in real deployed systems, you almost always have a combination of two factors. So first of all, you almost always only have hard black box access to the classifier. I can't get the weights of most deployed models, at least not easily. Maybe I could open up the chip and figure these things out, but I can't do that, right? I can't easily get the weights of some of these things. I mean, sometimes you can, like there was this famous neural hash break recently. So we'll get to that in a second. But, well, no, actually, sorry, I'll talk about that in a second if people want to. But for other things, like another example from Apple, right? Like Face ID on iPhones, you limit the number of queries you can do, right? So after a certain time, you require someone's password. You can't let them keep trying Face ID again and again. And just limiting the number of queries seems to be genuinely hard to break, right? So for example, Face ID on iPhones. This is the security of our iPhones, and they are still doing it with an ML-based system. There's a lot of different inputs, of course, to the system, but it hasn't been really satisfactorily broken using a pure adversarial attack mechanism as far as I'm aware. And the third point is just getting back to the point I mentioned earlier. Like, given number two, people are simply, there is absolutely no way people are going to be willing to sacrifice performance, the performance that we get from ML systems, for the sake of security, to some very limited and arbitrary, an unclear threat model that we typically use in robust machine learning. And so I think that these are all points that we need to take sort of very seriously about why people don't seem to be using these things in practice, and understand if and when these are in fact legitimate arguments to just go ahead and deploy ML as it is, and when they are not arguments to go ahead and deploy ML as it is. So the question kind of is, where do we go from here, to me? And this is actually my last slide. So this, this point, I just want to sort of pause and take questions. But to summarize the setting, I think, we have a current environment where there's a known and potentially exploitable security flaw in deployed models. It's true for software, by the way, too. But unlike, I would say actually it's much worse than software security, because we at least know in theory how to write secure software, right? We sort of know how to write software that doesn't have memory overflows and stuff like that. We're just really bad at doing it in practice. The flip side here is that in AI systems, we don't even know how to fix these issues. Even if we wanted to apply the absolute best practice, we would have no idea how to fix these things. And so I do think that we are setting ourselves up for the active deployment of systems that we know are flawed, and things can go wrong. But we need to understand, we need to shift to understand a little bit more, kind of practically speaking, what can go wrong, and when is this likely to be, in some sense, the minimum cost attack vector on these systems. And my genuine opinion here is I don't really know when this is, what are the trade-offs that would make these things kind of become, robust, become adopted, become all of a sudden the things that you actually want to do because it's worth it for the real attacks you see in practice. But what I will say is these trade-offs need to be more widely considered, and we need to sort of appreciate the trade-offs we are making in deploying the ML systems that we are deploying. So this is meant to foster discussion. We'll have some time later for discussion too. So I hope to have it. I see there's some chat questions too, but we can then just go from there. Oh no, this is the old chat. Never mind. All right. So thanks very much, everyone, and talk to you. So actually, Samesh asked about, can you use co-design like training for sparse rally activation? Yeah. So I was talking about these sort of the sparse paper. The short answer is it doesn't matter what you do. I mean, yes, you can try all these things. I think the person to answer that question would actually be Eric Wong, who is my former PhD student now, who worked on these relaxations and now works on the sparse stuff with Alex as a postdoc. But I think there is no easy fix here. I don't think we keep hoping for a magic bullet, some magic new architecture that's going to be genuinely secure in ways that nothing else even comes close. And all the progress in the field, every heuristic we have, every new advance we make suggests this is not coming. What we're going to get is a bunch of small, little, piecewise advances in robustness, and that's going to be the level of progress we have. So I think we need to accept that and understand where we go, knowing that that's the case.
Okay. Yeah, thank you, Zico, for the very nice talk. I learned a lot as well. And yeah, I do have some questions, but maybe we can leave to the end. And
great, yeah.
Yeah, thank you.